All right, so today the goal is to get to MDPs, which people who work on MDPs like to say that they're like much more real world than strips planning or classical planning ever was. So I just want to point out before we get to MDPs that classical planners can solve real problems too. Europa is a planner that was developed at NASA. And it's done real things. Like they use it to schedule the Mars rovers. So these are the Mars exploration rovers, Spirit and Opportunity. You remember those guys that were bopping around on Mars like way longer than we ever thought? There's a heart-rending cartoon. Have you guys seen the XKCD cartoon?
Yeah.
Oh.
I don't think I've ever had my heart rent.
Yeah, I remember.
Oh, we're not going to do it now because we have to talk about MDPs, but maybe at the end of class. So what they do, they plan for the Mars rovers on Earth, and then they uplink the plan. There's some amount of autonomy on board for short-range pathfinding, but mostly it's done on the ground. But they use a planning system because the vehicle has all kinds of crazy constraints that you don't want to violate. So they use a planner for that. Deep Space One was a mission that was part of the New Millennium Project, which was the idea is we're going to do really cheap missions instead of like a $1 billion mission. We'll do like a $250 million mission or something like that. Really cheap, so that if we can test out all this crazy new stuff, and if it doesn't work and we lose we lose the spacecraft, we haven't lost billions of dollars. We've just lost hundreds of millions of dollars. So, like they tried, what was that crazy new thruster they have? Ion thrust. Yeah, exactly. It's the amount of thrust is equivalent to the weight of a piece of paper on your hand. That's how much thrust this engine puts out. But it's extremely efficient. So you can keep the engine on all the time. And it turns out if you keep a piece of paper on your hand for like all year, the amount of thrust is like makes you go 200,000 miles an hour, which I don't know. I think people are intuitively not very good at multiplication, especially with small quantities. But apparently, if you leave your ion thruster on forever, it makes you end up going really fast at the end, especially given the amount of fuel that you take with you. And the NASA people hate having to take fuel up because it's really expensive. For every pound that you want to take up out of the Earth's orbit, it costs you $10,000 a pound or something to get something up. Really expensive. But anyway, so one of the things they did on Deep Space One, besides the ion thrust thing, was they have a planner, onboard planner, that controlled the entire spacecraft. They said, hey, go. And for a NASA person, that's radical because you never know what those crazy AI programs are going to do. So if it points the spacecraft towards the sun and the whole thing fries, then it's it would be the AI's fault and they'd feel bad. And the taxpayers would sue and Congress would shut down NASA and ban AI research and it would be bad for everyone. But they did give control over, and after an hour it crashed. It was a Lisp system, so they were able to log into the top level remotely and reboot, which I thought was amazing. But anyway, it worked. It controlled the spacecraft, did all the right things. So that was cool. I didn't know that they used Europa for scheduling the Hubble, but according to this website, of course, you can believe everything you see on the internet. They use it for the Hubble. Just cool. I wanted to talk about EO1. Now, I was under the impression that they use Casper for EO1, so maybe they do some stuff with Europa and some stuff for Casper. EO1, Earth Observing 1. So NASA's mission is not only to go explore the cosmos, but the whole justification for doing that, besides that it's very cool, is that it tells us more about Earth. So every once in a while, NASA has to put up a satellite that actually just looks at the Earth to make people feel like NASA's doing its job. So there's a satellite that takes pictures of the Earth, in addition to all the normal weather satellites and stuff. So EO1 goes around and takes pictures of the Earth, and there's limited bandwidth from satellites to Earth. There are few ground stations, and we have treaties with various countries like Australia and Great Britain and Iceland and stuff to put huge antennas on their soil. But still, even with that, there's a limited amount of time for downlink. So we can't get all the data off of EO1 that it captures. And furthermore, the data we can get only comes at certain times a day, whenever you're near a ground station. So whenever anything interesting happens, you're always really frustrated because you're like, oh, there's the picture from 2 days ago where a volcano's going off. Wow, let's get more pictures of that. But it was like 2 days ago, so it's too late. Or like, hey, there's this huge hurricane or something. Like, oh, it'd be really nice to have pictures at the time. So there's a planner that, in fact, there's a vision system that runs and looks at every picture that EO1 takes. And actually, a friend of mine worked on that. He did EO1. He also did dust devil detection for the Mars rovers. The Mars rovers have the same issue. There are these little. There is some atmosphere on Mars, I guess, but it's really yucky. It's like methane or something gross. I don't know.
Just incredibly
Thin. Okay, but they have like little whirlwind things, dust devils on Mars. These little tornadoes. They've spotted one in a photograph that like. We were taking a picture of some rock, and there was a little tornado in the background, and everyone's like, oh, wow, there are tornadoes on Mars. So we're like, oh, let's take more pictures of the tornadoes. But it's the same problem. It's like, oh, look, in the picture from yesterday, there's a tornado. Quick, let's move the camera there. But that was yesterday. So my friend wrote a little detector that detects tornadoes in pictures. And whenever they detect one, they take more pictures right then and there. Like while it's going, so that the next day when you downlink the pictures, like if they spotted a dust devil, they take more pictures. And same with EO1 with Casper. Casper has a volcano eruption detector and I think like big storm detector or something. And whenever it sees something interesting happening, I have no idea if they have like an underground nuclear bunker detector, but I would not be surprised. Whenever it sees something interesting in the picture, it quick after the satellite has now moved, and you have very limited amount of tilt in the camera on the satellite. You can go that way quite a bit, back and forth, orthogonal to the direction of travel, but to go back to whence you came is actually a little tricky. So you quickly slew back, so you're taking and re-image the same area if one of the detectors goes off. And that way they get more pictures of the stuff they're interested in. So the intelligence really pays off because you can't have a person up there at the satellite saying what's interesting or not. So they have an onboard planner that realizes, hey, we need to do this additional observation and puts it into the schedule in a way that interferes least with all the other pictures that the satellite or spacecraft is supposed to be taking. So I just want to point out, normal classical planners are awesome and wonderful, and if some MDP person walks up to you and starts dissing on classical planning, just tell them, what about all those great planners at NASA? So don't let them put you down. We had some end of lecture questions. I guess we should do those next. All right, Mr. Professor Person, have you actually written a planner using each of the algorithms that you taught us in class? Well, actually, I'm really embarrassed. The answer is not just yes, but I wrote the same planner, and I thought partial order planning was beautiful, because it is. The partial order planning algorithm is just gorgeous. It makes the fewest commitments possible. It instantiates just the actions that you need to fulfill some precondition. And so when I got a job out in the real world, someone gave me some problem. It was for that crazy printer I showed you. And I was like, oh, wow, great, I get to write a planner. I've always wanted to write a planner. I did this whole PhD in heuristic search. I never got to write a planner. So I'm so excited I'm going to write a planner. So, of course, I started writing a partial order planner. And, oh, my God, was it slow. It was so slow. It's unbelievably slow. It was wonderful fun to write. I did variable binding, and it was fabulous. It was a lifted plan. It was a lifted partial order planner, and to plan one sheet of paper through the machine took like 5 seconds. And of course, we're trying to do like 4 or 5 sheets per second, so that's like 25 times too slow. So then I said, oh, okay, well then I'll look at the planning competition. And if you look at the international planning competition, their planners, like Fast Forward is one of the famous planners, and it does forward state space search. So I said, oh, okay, I'll rewrite my planner. I'll make it a state space forward search. And I rewrote that, and it could generate a zillion nodes per second, and it was actually quite a bit faster, but it still wasn't fast enough. And then we hired, thank God, we hired an actual planning person to come onto my team. And he and I rewrote the planner to be a regression planner, and it turns out that if you're planning sheets of paper, the very most important constraint in the whole problem is that sheet 2 has to come out after sheet 1. Like, that's an extremely important constraint. So if you do all this planning and like, oh, this part of the printer's in use, I'll go to this other part. Well, there's other things being planned there. Well, should I go in front of them or behind them? You don't really find out whether you came out before or after the other sheet until you get to the very end of the plan. So waiting to test whether it's going to work until the very end means that you don't get very much pruning and you have this very deep tree and the planning takes forever. Whereas if you do regression and the very first thing you do is say, okay, here I am at the output after the previous sheet. Now what is the previous thing I did? You're always sure that you satisfied that final constraint. And anytime your plan actually gets down to the feeder, you're pretty sure you're going to have a valid plan and everything works out great. So the planner actually ended up being super fast and wonderful and awesome, but only after we had written in 3 different ways. So not only have I implemented a planner in each of the 3 methodologies, but I implemented the same planner in all 3 methodologies. And personally, that's actually kind of embarrassing because I probably should have realized what was going to be best first, but it was my first time doing real planning. So anyway, so yeah, I have.
Do you use OCaml for that?
Oh, yeah, of course. It's the best language under the sun. Was that a question, Dylan? Yeah.
Is there like a bidirectional planning?
Woo!
They had that for heuristic search. So I imagine.
Yeah.
Bidirectional planning. Yeah, so bidirectional heuristic search is a very is a fairly well-known algorithm. I'm not sure I know of anyone who's implemented a planner that goes bidirectionally. Bidirectional search is one of those ideas that seems, it's kind of like writing a theorem prover. It's the kind of thing like, seems like it ought to be simple, but when you actually get down to the details, bidirectional search is actually highly non-trivial.
Yeah, I guess you have to compare virtually every thing in both frontiers.
Exactly. Every time you generate a node on one frontier, you maybe want to be comparing it to all the nodes on the other frontier. And furthermore, even once you've found the same state, you may not have a guarantee that you found the optimal solution. So bidirectional search is really not very popular, not nearly as popular as you would imagine. Plus for search, for planning, it's especially weird because when you're doing regression, when we're doing forward search, we're searching in the space of states. Every node represents a state. When we're coming backwards, every node represents a set of states. Yeah, so we have 2 incomparable things on the different open lists. So, yuck.